Okay, guys, 2.6, graphs of basic functions. Okay, so what we're going to be doing in 2.7 is we're going to be starting to use transformations to get new graphs. So we need to get used to, I don't want to say the word memorizing, but we need to be familiar with some certain graphs. Okay, before we do that, I want to talk about continuity, which is a pretty important idea. And we say a function is continuous over an interval of its domain if its hand-drawn graph over the interval can be sketched without lifting your pencil. Okay, so that means it's nice and smooth. There's no breaks in the graph. That means we don't have to lift our pencil. So, example, describe the intervals of continuity. So I want to know, when is it continuous? So if I look at A, y equals, and that's not x squared, that's negative x squared. Notice that I could draw this and I would never have to pick up my pencil. It's nice and smooth all the time. So if I want to talk about when this thing is continuous, that's everywhere. So we're talking in reference to the x values, always the independent variable. So it's continuous on the interval from negative infinity to infinity, or you could say all real numbers. Part B, y is equal to 1 over x squared. That's what this looks like, okay? The thing I want you to notice is there's a vertical asymptote at x equal to 0. So if you've never seen vertical asymptotes, the thing to remember is, well, this is the place where we can't have an x value. And if you notice, what if I plugged in 0 down here? I'd have 1 over 0 squared, 1 over 0. You can't do that, right? That's why we have a vertical asymptote showing up here, okay? So in this case, I can be continuous here and keep going, keep going, keep going, and go to 0, but never quite get to 0. So this works pretty much like the domain in this case. In fact, the intervals of continuity exactly match the domain. The intervals of continuity are negative infinity all the way up to 0, but not including, union, everything starting from 0 but not quite 0, off to infinity. So a little bit different there. If we look at C, C is kind of interesting. C is what we call a piecewise function, okay? So notice we're going, and notice right here there is a hole in the graph. We actually call this a hole. That's what we call a removable discontinuity. Algebraically, I wouldn't worry about it too much right now, okay? As we continue on and we get right here, we have another discontinuity, but notice that we do have a value here for x equal to 2, okay? And then we continue on. I wrote this as what we call a piecewise function, okay? It is a function because if we do the vertical line test, we're fine, we're fine, we're fine. Now right here, I don't have a value here for x equal to 2. I have it down here. So that's fine. It still only intersects once. Then right after, I pick back up here. One way you could say this, and this is maybe not the most proper way of saying this one, is y equals x plus 1, because it looks like x plus 1. If x is less than 0, 0 is less than x is less than 2, okay? So basically, we're saying all the way up until 0, okay? And then anything from 0 to 2, and anything greater than 2. In fact, I don't like the way I mentioned this. Don't worry too much about how I labeled this piecewise function. That's probably not the best way. More so, I'm concerned about the graph, okay? And -1 if x equals 2, and you can see I have that right there, okay? So here, if I want to talk about the intervals of continuity, okay, if we look at this, this is going to be continuous from negative infinity. I would have to pick up my pencil when I get to 0, okay, union 0 to x equal to 2, because I have to pick up my pencil, pop down here, okay, and then I pick back up at 2, but not including, to infinity. So that would be my intervals of continuity. And continuity is pretty important, especially when you get to calculus, okay? But it is relevant for what we're doing now, too. So let's get started looking at the basic functions. What I want to start with is what we call the identity function. I'm pretty sure everyone's familiar with it. It's f of x equals x, or just y equals x. Notice that it's continuous everywhere, and we know its domain is all real numbers, and its range is all real numbers. So nothing too new there. Next one is the squaring function. F of x equals x squared, same as y equals x squared. And for this one, the domain, if we scan from left to right, there's always an x value, right? So our domain is all real numbers. And our range, we got to be a little careful here. The lowest this thing ever goes is the 0.00. The range we're talking about, the vertical part, or the y's. So we're going to start at 0. So to include it, I'm going to say 0. And it goes on forever upwards, so it's to infinity. Now, that's another one I think we're familiar with. The next one, maybe you haven't seen yet, is called the cubing function. F of x equals x cubed, or y equals x cubed. This one looks like this, okay? So you can plug in some points. I'll plug a few in here real fast just to convince you. If I put in 0, 0 cubed is 0, that's no big deal. If I put in 1, 1 cubed is 1. If I put in -1, -1 cubed is -1. That's where these 3 points came from. Now, what if I put in the value 2? Then I got 2 cubed, and that's 8. Well, there's 2, 8. And likewise for -2, -8. So you want to be familiar with this. Next question is what's the domain on this guy? Well, the domain is all the possible x values, so it is going this way. There's nothing I can't plug in for x, so our domain is the all real numbers, or -infinity to infinity. The range, this thing goes down forever, it also goes up forever, and there's no breaks in here, okay? So the range is also -infinity to infinity. All 3 of these so far have also been continuous, at least on their entire domains. Fourth one, the square root function. F of x equals the square root of x. For this one, okay, if I make a little table here, x and f of x, notice that I can't put in any negative values of x, okay? I mean, if I do, I'd get imaginary numbers, but imaginary numbers don't show up on real xy coordinate systems. So the smallest I can go for x is 0, because then we have the square root of 0 is 0. That's how I got this point right here. If I use 1, we have square root of 1 is 1. There's the 0.11. But since this isn't linear, I probably want to plug in a few more to see kind of what's happening. So the next one I chose was 4. So think about why I chose 4. 4 is pretty convenient because I know the square root of 4. Square root of 4 is 2, hence right here. And if you continue the trend, I could even put in x equals 9 and then 16. You'll notice that it's going up slower and slower and slower and slower as time goes on. Okay? So that's the square root function. The domain of this, if we want to say, okay, well, what can x be? Well, it can't be anything negative. It could be 0, so we'll start at 0. And it could be anything after that. We can take the square root of anything positive. So our domain is 0 to infinity. Notice it is also continuous everywhere. I don't have to pick up my pencil. There's no restrictions on x as I go that way. The range, also we have to restrict because we start at 0. We can never get a square root that gives us something negative. So for the range, that's also going to be 0. And even though it's going up slow, it does keep going up. So that's also to infinity. Okay.